An antiderivative to a function f of x is another function, let's denote it by capital F. When we take the derivative of this function, it should be equal to this one. So antiderivative of a function is a function which derivative is equal to the function. For example, if f of x is equal to 2x, then an antiderivative of this is x squared. Since if you take the derivative of this one, we will get this one. That is, take the derivative of this, we will get 2x, which is equal to f of x. And if f of x is equal to x squared, then an antiderivative of that is x to the third divided by 3. And the reason for that is if we take the derivative of f, then we should take the derivative of this one. Here is just a constant, so it follows along. And we take the derivative of this one, which is 3x squared. And now we see that the 3's cancel. So we get x squared. And this is just f of x. So we see that we take the derivative of the antiderivative, this one, we will get our function f of x. So if you have a function and want to find an antiderivative, you can just make a qualified guess on something, and then you can just test it. If you take the derivative of your guess, if it works, it's equal to this one, then you have found an antiderivative. So x squared is an antiderivative of that one. But that's just one example. We could have picked, for example, this one. This is also an antiderivative of that one, because if you take the derivative of this one, we will get this one. And we could have chosen any constant here. So if I take any constant here, c, and take the derivative of this, then c will just become equal to 0. So this becomes 2x. So you see that if you have found one antiderivative, then we can get infinitely many others just by adding arbitrary constants. So we can state this as a theorem. So if you have a function and we have found one antiderivative of that one, then there are infinitely many others that we can find just by adding a constant here. So to every function there exists infinitely many antiderivatives. So if you find one, then we find the rest just adding a constant. And that we can prove. So assume that we have a function f of x and we want to find an antiderivative. And assume now that we have found two different antiderivatives. Then we can form this function, the difference of these two. And if we now take the derivative of this one, we can just take the derivative of each of them. And now, per definition, this is equal to that one, because capital F1 is an antiderivative of this one. So this one must be equal to that. And the same for that one. That was also an antiderivative of f. So this must also be equal to f of x. But then we see that this is equal to 0. So here, inside the parenthesis, we have a function which derivative is equal to 0 for all x. And if you have a function which derivative is equal to 0 for all x, or for x in an interval, that means that the function is constant. So that means that this function is a constant function, and we can write that as equal to c. But then we see that these two functions just differ with the constant c. And that means if you have found one antiderivative, all others must be related to that one by adding a constant. And that concludes the proof. So if you have a function f of x, then this symbol here, per definition, means the set of all antiderivatives of that one. So basically that means if you have one antiderivative, then this is the set of all that we add to that antiderivative a constant c that is arbitrary. So the reason for choosing this notation we will come back to later. But this is just a symbol for the set of all antiderivatives of this one. This constant here is also called the integration constant. And the reason for that we will also come back to later, but for now it's just a name.